Stop for a moment before you sign off on that structural plan. Let's talk about one of its most critical components, the shear wall. It might seem like just another concrete element, but its role is monumental. It is the silent guardian, the steadfast soldier. When violent winds howl, when the ground shakes in an earthquake, the shear wall bears the brunt of the lateral load. It's the single element most responsible for preventing catastrophic collapse. A small oversight in design, a tiny construction error, can have devastating consequences. This topic matters because it's about more than concrete. It's about steel, public safety, human lives. So, what exactly is a shear wall? In the simplest terms, it resists lateral or horizontal forces acting on a building. Think of it as the building's spine. Columns, beams, handle vertical gravity loads, the weight of the building itself, its contents, its occupants. Shear walls are the champions of horizontal stability. Wind, seismic activity. A shear wall is essentially a very tall, very strong, very stiff, vertical beam fixed into the building's foundation. It ensures that when the building is pushed from the side, it does not excessively sway, twist, topple over. Typically constructed from reinforced concrete, masonry, materials known for their high strength and stiffness. The real magic lies in the combination of concrete with steel reinforcement bars. Rebar. Concrete provides immense compressive strength and rigidity. Steel rebar provides tensile strength to handle pulling forces, stretching forces during a seismic event or high wind. The effectiveness isn't just thickness or the amount of material used. It's intelligent engineering, precise engineering, making materials act as one cohesive unit to manage immense stress. One of the most frequent and dangerous mistakes in shear wall design is poor detailing. Detailing refers to the specific instructions on the engineering drawings that show how different structural components connect to each other. Critical connection, foundation below. Critical connection, floor slabs at each level. Critical connection, roof structure above. These connections are where massive forces are transferred. If these joints aren't incredibly robust, the entire system can fail. A shear wall alone isn't enough. It must be stitched into the building's skeleton. Weak detailing creates a break in the load path. When lateral force hits the building, it needs an uninterrupted path to the ground. A weak floor-to-wall joint is a faulty link in a chain. Under earthquake stress, that link can tear apart. Localized failures can occur, floor slab pulling away from the wall, concrete at the joint crushing and crumbling. Fix starts on the drawing board, with a focus on clarity and robustness. Engineers must provide explicit, easy-to-understand drawings for each connection. Specify exact size, specify length, specify placement. Anchor bolts, dowel bars, other steel elements show how rebar from the shear wall extends into and hooks within the foundation footing or the floor slab. Plan and draw tie beams, collector elements to gather diaphragm forces and deliver them to the shear wall. Never leave these critical connections to assumption or interpretation. Beyond detailing, two other fundamental mistakes can cripple a shear wall. Incorrect rebar placement, poor quality concrete. The rebar grid is the wall's skeleton, providing tensile strength to resist cracking under load. For this skeleton to work, rebar must be placed exactly per the design. Correct bar diameter, precise spacing between bars, proper concrete cover, distance from steel to outer surface, bars spaced too far apart, large unreinforced concrete sections prone to brittle shear cracking, bars too close to the surface, insufficient cover, vulnerable to moisture and air which leads to corrosion. Corrosion, rusted rebar expands, causing the surrounding concrete to crack and spall off. This is concrete cancer. Bars placed too deep inside the wall are less effective at controlling surface cracks. The fix: clear specifications and diligent on-site verification. Design drawings must show the rebar schedule, bar sizes, spacing, vertical reinforcement, spacing, horizontal reinforcement, required concrete cover. On site, workers must use bar chairs, spacers, plastic or concrete. These devices hold rebar away from the formwork. Before pouring, measure spacing and cover at several points with a tape measure or gauge. Low-strength concrete cannot resist the compressive and shear forces it will face. Causes of poor concrete quality: incorrect water-to-cement ratio, inadequate mixing time, contaminated aggregates or water, improper curing. Weak concrete will crack and crush prematurely under load. Fix: strict quality control for concrete. Start with a reputable supplier and specify the exact strength class required. Perform on-site slump tests on fresh concrete. Cast test cylinders from each batch. Lab test compressive strength after curing for 7 days and after 28 days. These numbers and tests ensure the wall behaves as predicted under stress. A shear wall, no matter how well built, is only as strong as the foundation it rests upon. A critical and often overlooked mistake is ignoring the dynamic interaction between the shear wall and its foundation. The wall's entire purpose is to transfer enormous lateral loads into the ground. This means the foundation must be designed to receive these forces and dissipate them safely into the soil without failing. A common error is a powerful shear wall on an undersized or improperly designed footing. Like building a brick wall on sand, the wall might be strong, but the base will give way, failing through rotation or sliding. During a seismic event, the base of the shear wall is subjected to a massive overturning moment, a force that tries to lift one end of the wall up while pushing the other end down. If the foundation is not wide enough, heavy enough, or deeply anchored enough, it can literally be ripped out of the ground. Another risk: differential settlement, where the soil under one part of the foundation settles more than another, inducing unplanned stresses into the shear wall above. The connection itself is also a point of vulnerability. Insufficient steel dowels connecting the wall to the footing can shear off under load. The fix begins with a thorough geotechnical investigation of the site. You must understand the soil's bearing capacity and its likely behavior under seismic loading. Create a footing system or a pile system that can safely handle vertical gravity loads, massive overturning moments, and shear forces from the wall. Explicitly detail the wall-to-foundation connection, with sufficient vertical rebar extending deep into the footing and properly anchored to transfer tension forces. Plan a clear and continuous load path, from roof to foundation, without gaps or offsets that force loads into weak elements. Beyond the primary foundation connection, another grave error is to ignore the myriad of other connections that make a shear wall part of an integrated system. The wall must be robustly connected to the floor diaphragms and to the roof diaphragms at every level. A diaphragm acts like a horizontal plate, typically a concrete floor slab or a wooden roof deck. When wind pushes on the building, or when an earthquake does, the diaphragm collects the force across its surface and transfers it to the shear walls. If the diaphragm-to-wall connection is weak or missing, that transfer cannot happen. The wall stands isolated. The diaphragm may buckle or fail, unable to offload its burden. Neglecting these connections renders the shear wall almost useless. The building's elements stop working as a cohesive unit. The fix is meticulous detailing. The design must include positive connections. Use steel collector elements or use drag struts. Embed them in the slab and weld or bolt them to steel plates in the shear wall. Alternatively, extend and hook slab rebar into the wall. These details create a strong ductile link that drags lateral loads from the floor into the shear-resisting element, completing the load path. A sixth, more subtle mistake is failing to account for out-of-plane forces. Shear walls are very strong in their own plane, resisting forces parallel to their length, but they can be weak when pushed perpendicular to their face, an out-of-plane load. This is true for long, thin masonry walls and for long, thin concrete walls. Wind pressure or seismic ground motion can create suction and pressure that push and pull on the wall face. If not properly braced, the wall can buckle sideways, much like a sheet of cardboard bending when pushed on its face. This failure can be sudden and brittle. Preventing out-of-plane failure means considering slenderness and providing adequate bracing. Make the wall thick enough for stiffness, Tie the wall back to floor slabs at regular vertical intervals so floors act as braces. For very long walls, add perpendicular bracing walls or pilasters to reduce unbraced length. The key: resist forces from all directions and ensure three-dimensional stability. Real-world examples provide the most powerful lessons in structural engineering. Consider the case of a mid-rise residential building that suffered a partial collapse during a moderate earthquake a few years ago. Post-disaster investigation revealed a textbook case of multiple design and construction flaws centered on the shear walls. Poor detailing at the wall-to-floor joints, improperly placed reinforcement. The rebar that was supposed to tie the floor slabs to the shear walls had insufficient embedment length, and in some locations, the rebar was missing entirely. This created a fatally weak link in the load path. When the ground began to shake, the lateral forces were not properly transferred from the floors into the shear walls. Instead, the connections failed. The floor slabs began to pull away from the walls. The shear walls themselves showed large diagonal X cracks. The concrete cover over the rebar was too thin, leading to premature spalling. The lesson from this tragic failure was stark and clear. Details matter immensely. A building is not a collection of independent, strong elements. It is a system that relies entirely on the integrity of its connections. In stark contrast is the story of a major hospital near the epicenter of a much stronger earthquake. The building weathered the event with only minor, non-structural damage, cracked plaster, fallen ceiling tiles, and remained fully operational. The key to its survival was a robust and well-executed seismic design centered on a symmetric layout of ductile shear walls. The designers meticulously planned load paths, provided strong, redundant connections between walls and floors, and a deep, rigid foundation system. During construction, every rebar placement was inspected. Concrete batches were tested consistently. The success of this hospital demonstrates the immense value of investing in quality design and construction oversight. Good engineering, executed with care and discipline, saves lives and preserves critical infrastructure. It's really that simple. Knowledge of potential failures is useless without a practical framework to prevent them. To translate these lessons into action, every engineer, site supervisor, contractor, adopt a simple but non-negotiable checklist for shear wall projects. This is not about adding bureaucracy. It is about institutionalizing safety and creating habits of excellence. First, review the shear wall layout. Are the walls placed symmetrically within the building plan? Balanced layouts minimize torsional, twisting forces in earthquakes, which can be incredibly destructive. Ensure walls are continuous vertically. Avoid offsets that create weak points in the load path. Next, focus on reinforcement. Before any concrete pour, a designated inspector must verify the rebar against the structural drawings. Check rebar size, check spacing, vertical and horizontal, use a tape measure. Check concrete cover, ensure spacers hold the cage off the formwork. Pay attention to corners and openings. Document inspections with photographs and a signed form. Third, connections. Inspect connection details at the foundation and floor levels. Are dowel bars from the footing extending the correct length into the shear wall? Is slab rebar properly hooked into the wall? Verify collector elements. Verify drag struts. Verify embedded steel plates. These connections are the handshake between members. A weak grip can lead to disaster. Do not cover these areas with concrete until visually inspected and approved. This is your last chance to get it right. Finally, material quality and construction practice. Is the concrete being tested? Confirm slump tests are performed. Confirm test cylinders are cast for significant pours. Review lab results. Are proper curing methods being used? Protect concrete from drying too quickly. Check that door and window openings are properly reinforced and that trades do not cut rebar for conduits. A proactive, checklist-driven approach turns abstract safety goals into concrete, verifiable actions on the ground. So, just do the checks. In conclusion, the The shear wall is far more than a simple structural element. It is a lifeline. It stands as the primary defense for a building and its occupants against the powerful lateral forces of wind and earthquakes. Its performance under pressure is a direct reflection of the care, diligence, and expertise invested during its design and construction. As we have seen, the path to failure is paved with common, avoidable mistakes: poor detailing, incorrect rebar placement, weak concrete, inadequate foundations, broken load paths, lack of quality control. They represent a failure not just of materials, but of process and professional responsibility. However, for every potential mistake, there is a clear and achievable solution. The remedies are not complex or mysterious. They are rooted in engineering fundamentals. Follow the building codes. Design robust and clear connections. Specify appropriate materials. Demand rigorous quality control. We can learn powerful lessons from past failures and successes. Meticulous attention to detail at joints and connections is not optional. A disciplined construction process, verified at every critical stage, separates resilience from vulnerability. The tools for success are in our hands. This brings us to a final, urgent call to action. Do not let this be passive reading. Act now. Pull out the shear wall plans and check them again. Ask a trusted colleague to perform a peer review. Create a simple one-page checklist and make it mandatory. Champion pre-pour inspections. Explain the why to your team. Protect lives. It's the most important thing we do.